Y nos va a hablar sobre el problema de Plateau de Allen-Cahn. Muchísimas gracias.
Okay, thank you. I think I speak in English, right?
Okay.
Yeah. You want to speak in Spanish?
It's
up to Steven.
Oh, I think you should do it in Spanish.
You want me to? You want me to in Spanish?
He knows. Something.
He knows. Yeah, no, I'll do it in English because you're recording.
Okay.
But yeah, if I do Spanish, you can do Italian. This is taking Italian. Okay, so let me begin. So thank you for the invitation. I should say thank you. It's always good to be in Granada. Yeah, I don't know which. I think it's my maybe 6th or 7th time in Granada. It's always nice. I'm always happy to arrive here.
I would hope not to be the last one.
Yeah, no, definitely not. If I don't come to work, I'll come to visit.
Yeah, sure.
That's true as well.
Let's evolve.
Yeah, let's evolve. So yeah, we're going to talk about this connection or approach to the Plateau problem via the Allen-Cahn equation. So I want to talk today a little bit about what this means. So let's begin discussing what do we mean when we say the Plateau problem. Because the term Plateau problem has been used to refer to a wide variety of problems in geometric analysis, some of which we won't talk, we won't say anything today. But just to mention, the plateau surfaces that one observes in nature, sometimes they have singularities and they have these triple junctions or other strange behaviors, and often the Plateau problem considers all this. It also considers the parametric case in which you fix, say, a topology and you want to produce a minimum surface with that topology and a given boundary. That's also a type of Plateau problem that's often referred to as the parametric Plateau problem. So we're going to talk about that. So what we mean by the Plateau problem is the following. So in this theorem, given, so this is just one instance of the type of theorem we're considering. So if you have a curve in R3, so say a smooth curve, which is possibly disconnected, right? Then there is a surface sigma 2, so two-dimensional, such that first the boundary of sigma is gamma. Second, sigma is minimal, is an embedded minimum surface, which is smooth up to the boundary, right? So the boundary is not just a topological boundary, but it's a boundary as a surface, right? And 3, sigma has the smallest area among all surfaces satisfying 1 and 2. That's the key thing. Is, you hope to produce something that is embedded and that is smooth up to the boundary. Okay. So pretty much the emphasis is on the regularity rather than the topology, right? So the boundary gamma here can be very complicated, and depending on how complicated the boundary is, the topology of sigma will have to change to, adapt to that. So let's just draw some examples of what to expect. By the way, so we're giving this seminar, and we hope that we take it easy. So, interrupt at any time and ask as many questions as you need. There's no rush. So I think that what we can use this opportunity is to really understand what the limitations of the theory is, where can you apply it, and etc. So if you have any questions, interrupt me at any time.
Gamma prime is gamma and the curve is close.
Yeah, I mean gamma 1. So like, when you write sigma 2.
Okay,
the
the dimension.
It's just the dimension.
Okay.
Yeah.
Yeah, actually close, right?
Yeah, it's a closed curve,
Great.
possibly disconnected. It needs to be a boundary, right? So the simplest example is when gamma is just and it's 1, a flat is 1. Then in this case is really nice because the solution is just a flat disk, which is minimum, and it's also the only minimum surface we can start in any possible sense. Another example that might be familiar is probably familiar to most of you is you take 2 of these S1s, then you have, if they're close enough, then you have a catenoid as a solution. That would be also an example, right? So in this case, it's disconnected, and the topology needs to change. In this case, you can also have the example, of course, there is the 2 disks. And as some of you might know, there's a third catenoid in between these. That's a kind of min-max. There's a simple way of constructing new examples, which has to do with something called the bridge principle, which is if you have already a solution to the Plateau problem, which you know is minimizing, you can attach a bridge to the boundary, and if the bridge is small enough, then the new boundary will have as a solution of the Plateau problem the union of a strip plus with the previous solution, right? So in this case, we have a connected boundary. So here the boundary is topologically is 1 again. So you see is this curve as part of it. So it's connected. So this in itself is interesting because, well, let me just give you other examples quickly. So another one that illustrates other aspects of it would be something like this. You take 2 strips and glue them to each other, something like this, right? So then you understand what the picture is. Right. So in this, if you take this boundary, well, if you look at it carefully, you will convince yourself that the boundary is connected. It's again as 1, and that right because you can just follow this and back to the same place. But you can have many solutions because instead of gluing the strips, you maybe can glue a disk here, a disk on the other face behind, and then this strip, something like that. So you have many minimum surfaces with this boundary that are easy to construct. So in this case, it's also connected. And then another example that I want to mention is that you can take a tiny strip, right, and then do the usual trick to produce a Mobius band. And in this case, of course, this is S1 topologically. And the sigma, in this case, is non-real. In this solution of the Plateau problem, we need to allow for sigma to be non-orientable sometimes. That's the most efficient surface that spans this boundary that you can find. Okay. What is interesting about this, just as a side comment, is that if you pay attention to this boundary, you will see that this is an unknotted boundary. So the boundary, the top part, for example, was like this. stuff there. You can clearly just twist that. So the boundary itself is unknotted. So I think that's interesting. Gamma is unknotted. Does it have two T's? I'm not sure if it has two T's. So why I find this interesting? Because topologically, these three examples, or I guess these four examples that I drew, I'm not going to do that. You get the idea. They are all S1s, and they're all unknotted. So there are isotopies that take you from here to all these situations. Okay. So an interesting question in the Plateau problem has been, when you do these deformations of the curve, when does this new type of solutions arise? Okay, this is something that relates to some work that Brian White has done, relating, for example, the total curvature of the curve to the possible solutions that you can find. Okay. This question, because in this case, it's the unique minimal surface. Sometimes the solution of the Plateau problem will have triple junctions and other kind of things that also arise at some point. So this is, I think, an interesting open question, finding conditions on the curve that prevent, say, triple junctions or prevent non-orientable objects. In the case of Brian White, he did the non-orientable case. And he used the mean curvature flow for this. It's one of the applications to the mean curvature flow to minimal surface theory. He found a concrete bound for the total curvature. Okay, so anyways, that's just to illustrate the wide number of questions, or different type of questions that you can make. But again, we're just going to focus on this theorem. And what we want to provide is a new framework to study this problem. So let me just mention quickly a few of the frameworks that exist. So the first one, perhaps the oldest, is the theory of orientable currents, or I should say just currents. You know, people will just say currents, but I just emphasize in their oriented objects. So these will have coefficients, set, or not set n, or set p, and greater than 3. And related to these is what people call flat chains mod 2. They are sort of currents with coefficients mod 2, but they have a different name. And then, you know, some people that have worked on these two things that I should mention is originally the work of Federer and Fleming. Then the theory of Hart and Simon, and Brian White, and perhaps some theorems, and many other people. Right? I'm not trying to be exhaustive here. I just want to give you the idea that this is, you know, it's been an important subject that many people have contributed in different settings. So I want to especially highlight these two because in the simplest case, which is coefficients in set, Federer and Fleming, they invented currents essentially to solve this problem. And Hart and Simon, they proved the regularity theory at the boundary. So this is kind of a theme in the subject that you have to, you know, the regularity of the problem at the boundary requires techniques that are slightly different from the ones in the interior, and you need, you know, it's a delicate issue. And then what we're going to present today is another approach that I choose to call here the level set approach. For example, we have the Allen-Cahn, but I imagine slightly different versions are possible. And then in this case, this setting was introduced by the work of Freud and Struve, which dealt with the interior, you know, maybe presenting the setting itself and proving that you obtain a minimum surface that in the interior is embedded. But they were not able to prove that at the boundary you're also embedded. So that's what we've done together with Stephen Lynch. We've completed the picture to show that in fact you obtain something that is embedded, among other things that we'll talk about. Okay, so let me tell you what the Allen-Cahn equation is. So this is it for the Plateau problem. And do you have any questions about the Plateau or these theories? Yeah, in a big sense, I think the level set approach and the flat chains mode 2, they have a lot in common in terms of the objects that you produce. Okay, this setting of orientable currents requires you to orientate the boundary, and depending on how you orient the boundary, your solutions can be a little weird. For example, in this case, you have, say, your boundary is two circles, right, which can be oriented in the same way or in opposite ways. If you orient them in opposite ways, then the solution given by orientable current will be analogous, right, minimum analogous. But if you orient them this way, then what you obtain is two disks essentially on top of each other. One with multiplicity 2, and then the outside analogous with multiplicity 1. Okay, so the regularity theory of Carl-Simon tells you that at the boundary, you always see on one side m planes, and on the other side m minus 1 planes. But otherwise, everything is smooth. However, the flat chains mode 2, you only see this as a solution, okay, which have multiplicity 1. So this doesn't guarantee multiplicity 1. Okay, so now let me talk about the other side of the title, which is the Allen-Cahn equation. And I think it'd be helpful for us if we can think of it in the setting of general manifolds, right? Because there's some ideas that I would like you to understand about our approach that are easier to say in the context of manifolds, of closed manifolds, mainly because closed manifolds have no boundary. So a few arguments are kind of isolates the question. So what is the principle involving the Allen-Cahn? It's something like this. So if a function u, say from a manifold R, satisfies an elliptic, a semi-linear elliptic equation, so something of this form. This is, again, it's a very general. In the future, I'm going to choose a specific f. Some things will be more precise, but this is a general principle. It's really just about any semi-linear equation. Then the level sets, and again, this is any level set. The principle says that level sets of this equation are very similar to minimal surfaces. And this was a fact that was noted by the Jordi, and that has been exploited in many ways.
There, you mean regular level sets or all level sets?
All level sets.
All level sets.
Yes.
Even the critical.
Right, but keep in mind this is a very soft principle. So when I say minimal surface, maybe I mean something that can be singular, can have singularity. Okay. So even level sets that are not embedded will still be like, say, for example, the intersection of two minimal surfaces, which is not an embedded object, but is still minimal in the sense that the area of that will grow to a zero, to change up to a zero. So for now, just accept this as a general norm to look forward. But what I tell you is part of this principle is the fact that the larger, and again, being very informal, the larger m is, the closest the level sets are two minimum surfaces. This is kind of the
Precision in what sense? In the
Big.
volume?
big, yeah. So if you have an M and you make it larger, then the level sets are closer to minimum surfaces than were before. That's the principle. Or in other words, you can think of these. I'm just trying to give you like a set of rules that you can use to test specific situations when you're thinking about an Allen-Cahn equation. So one example of this will be the following. If I want to find a solution of the Allen-Cahn equation whose level sets look like a specific minimum surface, and this specific minimum surface has a lot of curvature and maybe it's too intricate, I will need a lot of room to fit my U correctly. Okay? So that has to do with this larger idea of larger. I wrote larger.
Yeah. You went up here.
This is a subliminal message.
It went up.
Okay. Yeah, so this is just a general principle. Let me be more precise then. And then your question will be answered. At least partially. So more precisely, so we choose a specific, etc. So for example, f of u is equal to u3 minus u, which is the derivative of a function w that is a double well potential, is called something like this. It's a function whose graph looks like a w. And then the observation is that u satisfies this equation. U is a critical point of an energy which is given by so what I'm saying is that this elliptic equation is the Euler-Lagrange equation to this function. Okay. And then rather than making M big, right, we introduce a parameter epsilon, and then we can write the equation as, I'm going to save some time just by writing here. By putting say epsilon squared here, epsilon here, epsilon here. And what that does is this is equivalent to solving this equation without the epsilon in it's a geometric dimension epsilon. Okay, so in this sense, when you're looking at the Allen-Cahn equation, you're really just making more and more room so that you can hope that your object has level sets which really in the limit become minimum surfaces. Okay. Okay, so that's the remark. And then in this context, what we can say is that as epsilon goes to 0, the level sets converge to a minimum surface. Not a very precise statement, but let's make it more precise later. So in this context, as epsilon goes to 0, we have that the level set of this, which by the way is, so note, U is really U epsilon. So for every epsilon I have a different U. But I'm not going to write the epsilon because we don't need to be. So to emphasize that, then this U epsilon equals 0 converges to a minimal hyperspace. So we need to talk about what this means. You know, for example, what do I mean by minimal surface? What do I mean by convergence?
The role of 0 is not relevant.
The role of 0 is really not relevant. As I said before, you really use any level set, and there's a few reasons. I mean, besides symmetry, which is the main one, I guess, why you would choose to focus on 0, because this function is symmetric around 0. It's also where this has the highest energy concentration, right? Because this function is like this, and this is 0, and the solutions are always going to be between -1 and 1. So that's where your energy is concentrated. And but you can pick any constant between 0 and 1, and that will work the same. So I would say this: in some sense, you will expect that level set. They will all converge to the same minimal surface, but this will converge fastest. In some sense. But very, very minor difference. So the remark, multiple notions. For example, I'm of minimal surfaces. I'm of minimal hypersurfaces. Right? For example, the convergence could be the sense of Hausdorff, meaning as a compact set, or in compacts, this closed set converges to this closed set in Hausdorff distance. Maybe the minimal hypersurface is not really an embedded surface, but it's a manifold. Or maybe in a really nice case, you know, everything is smooth, this is embedded, and the convergence is graphical. So there's really a wide variety of notions of convergence that arise in a specific context. You know, sometimes you cannot avoid talking about variables. But in most reasonable situations, you can, which is what we're talking about next guy. We're not going to talk too much about variables. We'll talk a little bit about it. But in the situation that we're focusing on, we are working with minimizers, and that's the best situation usually, where we have the strongest convergence. Okay, so let me talk about that. Interior regularity. It's called interior because I'm thinking that this is what's going to happen when we talk about the Plateau problem away from the boundary. So interior regularity. So that omega is an open set, a manifold, and assume that for every epsilon, you know, you have that U minimizes U, say locally in sigma, and by that I mean that the energy of U plus a function always cannot decrease the area, and then this function is saying W1 to 0 of omega, meaning, you know, maybe we can even put this something like that, you know. It's a small perturbation that is compact. Okay. 2, assume that the object is bounded, which you don't really have to assume, but I'm gonna just write it in this. So the supremum of the energy, when it's integrated just on this set, is finite. Then, and then, by the way, I'm here in M3, is in dimension 3, making things concrete. Then there exists the embedded area minimizing minimum surface sigma such that U equal to 0 converges to sigma reference. So this theorem was known a long time ago in the 80s by the students of the Georgie, Monica and Martola. This is quite of a curious thing. I would never actually. So this was published in some small, I mean, I don't want to say obscure, but it's really, I guess, inaccessible in standard ways. Italian journal, which you cannot find online. So I haven't been able to find the actual reference. But, you know, this is well understood. There's some work that Cafferini did that improves the regularity of the minimizers. There is the work of Cayley-1 that proved like LAR type estimates for multiplicity 1 solutions of the Allen-Cahn. So there are many modern ways of proving a statement like this. Great, so this will be the main regularity that we should keep in mind on these mini curves that we'll use. Okay, so let me just talk about some heuristics about the Allen-Cahn equation. So in one dimension, we have what we call the model, I'm going to put here the Imperial model solution. Right? So in 1D, the equation becomes an ODE. And there is only one interesting solution. There is only one, up to translations, of course. There is only one entire finite energy solution, which is not constant. And that is ut equal a hyperbolic tangent. There is some constant here. I think the constant is 1 over square root of 2, but maybe it's square root of 2. I mean, it's easy to figure out, you can just differentiate this. But the point is, and of course, if you put an epsilon, then the constant depends on it. The point is that the solution looks like this. So it goes to -1, minus infinity, and it goes to +1. So I think you've all seen this before. So let me not spend too much time on this. But this is relevant. So what I want to emphasize is this, right? This is really a model solution. And what do I mean by that? So let's look at the higher dimension case, and then we can see. So in dimension n, so n dimensions, maybe you have a manifold like this, and then you have sigma there, which is the minimal surface. Then you expect your u to be close to -1 here, close to +1 here, and then u equals 0 is in some sense close to sigma. And u itself should look like the one-dimensional model solution along along directions normal to directions normal. Okay, so you should think always as of the Allen-Cahn equation as a sort of field of model solutions that you're moving along a minimal surface. Okay, and then a little bit working with this equation is figuring out, if you want to construct solutions, how to arrange these fields correctly so that you're very close to a solution, and then you can use standard methods to converge the solution. Or if you're trying to prove regularity of the nodal set, this is the picture that you have to keep in mind. This is what you can expect to see, so this informs your strategies. Is this okay? Okay. Much of the regularity theory comes from how well behaved this model solution is. For example, is it stable? The Jacobi operator has an identifiable kernel, which there's a spectral gap after. So the first eigenvalue is 0, which is stable, but it's degenerate. But you know what the kernel is precisely, right? It's the derivative of the tangent, hyperbolic tangent. So you see, because the function is monotone, if I differentiate, then I get a positive object in the kernel, right? Which is the derivative. And that tells you state. But the other thing that this does not tell you is that there's a spectral gap. After the 0 eigenvalue, you have a second eigenvalue, which also has an eigenfunction that is explicit. Okay, and that's good because it allows you to invert things that are orthogonal to the kernel. So the way this regularity theory works is usually you try to decompose test functions into parts that are tangential, which you know exactly what it is, tangential to the kernel, because you know what the kernel is, and parts that are orthogonal to the kernel, which can be inverted by the operator. Okay, so that's just in a nutshell how the regularity theory works. So the remark is that there are many ways. I'm not going to write this. I'm just going to say there are many ways in which minimal surfaces and solutions to the Allen-Cahn are really the same thing. Okay, so a few examples are the work of Allen-Cahn and Imperial, which gives if sigma is non-degenerate. So think of a maybe compact minimal surface in a closed manifold that is non-degenerate and separating. Is important. Then it's minimum, right? Everything is minimum. Then there exists a solution that converges to sigma graphically. So at least generically, whenever you see a minimal surface, you can produce a solution of the Allen-Cahn that will have that surface as a in the other direction, there's work that I did a long time ago now, which tells us that if the solutions are well behaved in a kind of soft sense, so for example, the energy and the index is bounded, then U0 converges to sigma, that is a smooth minimal surface. Right, so I'm just talking again on dimension 3. This statement is also true for hypersurfaces up to dimension 7, but let's focus on dimension 3 for now. And then I wanted to mention, because I think it would be interesting for people here, is that the work of Delpino and Kowalczyk and Wei they do the same thing as in one. So they construct solutions, but same as parameter, but for surfaces that are entire minimal surfaces in R n, for example in R3, that have finite total coverage. Right, so for example, something like catenoid, coastal surface. There's also work they did for producing a solution that looks like a Simon's cone. But what I want to say, and then maybe this is interesting to say, in Pocar-Victoria, the solutions have to be non-degenerate. This, of course, is not possible in R3 because you have a lot of symmetries, but their hypothesis is that if those are the only elements of the kernel, so rotations and translations are the elements of the kernel, then you can construct a solution.
How old is the convergence in the second item?
So in the second item, yeah, that's a good point. So in dimension 3, in some circumstances, now thanks to the regularity theory of Chodos and Montoulides, we can say that the convergence is graphically. So this will be the case, for example, generically. So in some sense, if you're in a bumpy metric where there are no degenerate minimal surfaces, the solutions described by 2 should be the same as the solution described by 1. So the convergence is very graphic. The other circumstance where we know this is in Ricci positive. Okay.
Bubbling cannot happen.
No, there's not a. Do you mean like multiplicity?
Like rescaling of any non-flat object.
Yeah, no, this doesn't happen in this situation because if you rescale, say by epsilon, you always have the same equation, right? So you always go back to that model solution in some sense. Right? So how does the theory work in that case? You classify stable solutions in R3 of the Allen-Cahn. There's only one, is the copy of the model solution over a plane, right? Then, if you have any stable solution in a compact manifold, when you blow up, you always see a plane, okay? So there's not going to be anything different coming up, okay? These should be different in higher dimensions, okay? Because you can have, dimension more than 8, you can have the Simon's cone, and you can have this. So far, that regularity, it's only known for dimension 3, but it's expected to hold until dimension 7. Okay. Good. And then, so again, only Ricci positive. So I don't know, in other circumstances, you can produce, in a torus, for example, a flat torus, you can arrange some configuration of minimal surfaces that, because it's not symmetric, it won't be obtained as a limit of Allen-Cahn. So up to what extent these analogy breaks when things are not generic is really not understood. Okay, so yeah, so I think the main point here is where the symmetry breaks is that the solutions of an elliptic equation, they're really entire objects, right? If you modify your metric a little bit here, the solution will change slightly everywhere. This doesn't happen for a minimal surface. So that will allow you to construct things that at least you can localize the behavior of the equation in some sense. The Allen-Cahn is going to try to pick something that looks nice globally. Okay? But what I wanted to say about this is that in one, in Pocar-Victoria, I emphasize the fact that the surface has to be separated, right? And this is because, it's a function the image in R. It's always separated. So if you have good convergence, the minimal surface has to be separated, otherwise this won't make sense. So this is the one of the challenges with the Plateau problem is how do we make sense of this, right? Because if you want to converge to a surface with boundary, this is not separated. Right? So I mean, this side here is the same as the one inside. So how do you make sense of this? And this is what the Frulich and Struve did. So this is their setting. So there is a canonical way of turning non-separated objects into separated, right? And the way this works is via a double. It's kind of similar to saying if you have something non-orientable, you can always kind of work with an associated orientable object, which is the orientable double. As in this. So I want to explain how that works because that's the core setting for us. So let me just tell you the construction, which I feel like. It's funny because sometimes I talk about these things to people that have more background in PDEs, and sometimes like there is very strong image guidance. So the parts that the audience finds difficult are very different in different settings. So let me just tell you the geometric construction and see whether you believe me or not. So let gamma be an embedded closed curve, which has maybe many components, right? So many curves in space. And then sigma is an embedded surface with boundary big M. And then we can call the ambient space here, that is going to be relevant M, which is R3 minus gamma. Okay, so our surface kind of lives inside of this space, and I've removed the boundary. So definition or construction, I'm going to denote by M tilde at this joint union of two M's, right, glued via sigma. Okay, so I'm going to, so this is the space obtained where we glue copies of R3 minus gamma along sigma in such a way passing through sigma takes you, I guess, one copy of M. When I explain what this means first. When I explain what this means. But I think maybe some of you already have a picture in mind. This is a common construction that one does in certain situations when you're gluing, when you have cut a manifold along a surface and you want to go back to itself and reflect or something like that. So how does this look? I have M, one copy of M, and I have the other copy of M. And then I have maybe gamma here and gamma here. So M is really just a complement of the curve. And I want to glue these two together. So what I told you before is that there is a surface. I'm gonna make purple. So there's two copies of the surface on each face. And the way you're gonna glue is like this. You're gonna identify, say, locally, when you go around the surface, because it's embedded, it does separate more. So you take the upper part of the ball, and you glue it with the bottom part of the ball. Right? With being careful, of course. So for example, if this ball contains sigma, then the lower part does not contain sigma. And then that way you can glue it because it's packed just the same way. And of course, you do the same thing from below. There's going to be this neighborhood that remain, which are going back with this neighborhood. So every time you pass through sigma, you change from here to here. It's kind of like a portal. There's a game called Portal, if you're familiar. Exactly the same. Right, so the remark, I hesitate calling this exercise. It's an exercise, a simple exercise, to like from topology, right? To prove that this is indeed a smooth manifold. So until that is a smooth manifold, and the projection that says until that the M is a double cover.
No, es que está nuestro compañero.
I can have a for the test. Here. Moreover, and this is the relevant part, sigma tilde, which is the unit of sigma, is separated. Right? So sigma tilde is now these two surfaces. And it separates because it's separating one copy of everything. Okay. Again, this takes a little bit of time to get used to it, but that's the key. That's the key concept. So what this allows me to say is that now there is a function, regular function. Now, so there is u tilde, r, such that, well, it's a nice function in W12. This is relevant because we want things to have finite energy. But also restricted to sigma is exactly 0. And if it's not 0, in the complement.
So what happened with the metric?
Oh, the metric, just do the proof of metric. I mean, the M is the same, it's literally the same metric. So you can have it with the same metric.
Sigma is regular.
Huh?
Yeah, really. Yeah. Sigma is. It's okay, right?
Yeah, because you see, you took this ball. Here there was a ball, the union of these two caps. One cap is open and the other is closed, so you can cut it.
Yeah. Okay.
The union is a ball, and then you took one from here, one from there. So when you put it back together, you don't know they come from different spaces. Right? It's really right. Does that make sense?
Yeah.
We can spend some time on this. I'm happy because I think it's important to have it clear, and it will be very easy to convince you. I think, as your all your methods.
So this is a Riemannian program.
Yes, Riemannian cover. This is a local isometry. P is a local isometry. This is a double cover that has all the good properties that you can ask of a cover. Okay. So, but the point is that because now it separates, I can construct this function. And the key observation here is that u tilde is up in the sense that u tilde composed with tau is minus u tilde, where tau is the only deck transformation that is covered. All right, so the deck transformations here are just the group set 2. This is the only element. That's non-zero. That's not the identity. So it's the map that says from here to here. So in fact, you can construct a function like this by simply defining u tilde of x as the sine times the distance to sigma theta. Yeah, maybe you want to put. I think I'm. Right? Because you want it to be bounded, so that you have finite energy. So yeah, do you still have more time?
Yeah.
What do you think? 5 minutes? On this?
Until 2, you can continue.
Until 2?
Oh, yeah. You finish with 1.
Oh yeah, it's from 12:30 to
Yeah.
2.
But if you
No,
want to
that's
finish in the
perfect.
minutes,
That's perfect. That's perfect. I was confused. It's 2 hours.
It's 1 hour and a half.
Yeah, 1 hour and a half. More than 1 hour.
But you can finish before you.
More than 1 hour. No, I'm not. I want the opposite. I want to keep you here forever. No, that's good. I got a bit confused. Okay, so what this tells us is that double covers are relevant for the construction because then you can, there's a few things, right, that I would like to say that quickly, I think for you to understand. First, double covers are relevant, but also doing a double cover is a bit of redundancy, right? Because my function has dissymmetries, right? So the right space where you would like to work is a space of sections, which is the quotient of all the odd functions, you know, on this space M tilde. When you quotient all the odd functions, you have a line bundle over this original base space, which is R3 minus the curve. And your odd functions now correspond to sections on that bundle. Okay? So that's what we're going to cover. But before we get there, I want to talk about the classification of the outcomes. Classification. Right, so there is this Galois correspondence, people call it, but I think maybe that's misleading because the Galois really work on fundamental groups. I don't know. But a covering map, a covering space, is a double cover. Actually, maybe in Spanish you have a different name for this. Is a double cover in H, which is the group image of the fundamental group of the cover space. Is a subgroup of index 2 of G, which I'm going to call. Okay, so in other words, what I call, I've seen called Galois correspondence, so that's the name in, for example, Hatcher's book, is that the normal subgroups of the fundamental group are in bijection with normal colors, okay, which are the nice colors. There's a bijection, and this is called Galois correspondence. And of course, the word normal there is relevant, but here what is good for us is that as a group of index 2 is always normal. So that's fine. We don't have to worry about group theory too much. And then, moreover, since set 2 is abelian, as abelian group, the quotient G by H, which is 2, splits as, I'm gonna write here. So we have phi 1 of n, the fundamental group of n, and there is a universal map, which is the organization of a group, right? So you can take a group that maybe is not a billion. There's a canonical, the largest a billion group or something like that. It's not good to say the largest, but it's going to be a group together with a map, right? And this organization together with the map have a universal property. And the property is that any map that goes to an abelian group factors into this map plus something else. And the other fact that you might know is that the abelianization of the fundamental group is the one homology. Okay, so this is H1 of M. This is the abelianization of the fundamental group. And this is some homomorphism to set two. Right? So a map to a abelian group factors this way. So what I mean by this is, and again, this is just a little detour we're gonna do to group theory to just make a point that there's only one relevant cover that we have to look at in any given situation. If you give me a set of curves, there's a unique cover. So it doesn't matter if I'm looking at a surface that is a torus, but it has a boundary, that has genus 100, has a boundary. They all arise as surfaces in the same cover, as separating surfaces in the same cover. You see, because you might think that that construction depends on sigma, because I use sigma to glue. What I want to prove to you is that that's not the case. It's the same, regardless of which sigma you use. Okay, so the point here is that the kernel of so H is the kernel of that map. So it's phi because we have minimization. And P is determined by the image of the generators of H1. So this is H1. Okay, so why is this good? This object can be really complicated. So even if you have one curve, if the curve is knotted, this is a famously interesting object for people in math theory that can be very complicated. But as soon as you abelianize, it becomes very simple. So this group, H1 of R3 minus gamma, is always k copies where k is the same k as components. Okay, so this is to say the following. So now the generators, I should make a drawing, are going to be like this. So maybe this is a curve, then maybe I have some crazy knotted curve, and I'm considering this is gamma 1, gamma 2, on a minimal surface with this boundary. Then what this theorem tells you, by the way, this has a name. This is called Alexander duality. It relates the homology of, or a homology of the complement of a manifold to the homology of a tubular neighborhood of the manifold in another complementary degree. That's why there's a duality. And you see the homology of a tubular neighborhood of a curve is very simple. So that's what you obtain. But anyway, so the point here is that the generators, because it's associated with this tubular neighborhood, are all these curves that have a simple link with each boundary. Okay, so these are the generators. So if you want your surface to span the boundary, you have to send all the generators to 1. Right? So remember, this group is just 2 elements. So if you want to see it, you send it to 1. And this, of course, gives you a unique homomorphism from the organization to 2, which in turn gives you a unique double cover. So that's kind of the idea. Any questions? It's a bit of a detour, but necessary, I think. It's the final uniqueness of the construction. There are not many double covers. So this is a more general fact, right? In a closed manifold, the number of double covers is in correspondence with the number of homology of hypersurfaces. So every time you have a homology class for hypersurfaces, you have a double cover. Okay. So you can find a double cover of RP3 that will have a section, sorry, a line bundle that will have a section whose 0 is the RP2. Things like that. Okay, so now I would like to talk about line bundles. This is brief, bundles. Okay, so as I said, the information on a double cover is redundant. That's why we quotient this information. We obtain a line bundle. So given gamma and 3 is above, we denote by L of gamma, also L of M, I guess. L of M minus gamma. Sorry, L3 minus gamma. These are all the same. The unique, the line bundle, by quotienting, I don't know if that's a word. By quotienting the odd functions, sorry, let me be more precise, is the line bundle over M obtained by covering, by quotienting, sorry, the space of odd functions I guess I could say this better in this context. So you quotient M tilde plus R by the action that sends a point and a number to minus the point. Okay, so this is more direct. Yes. But in a sense, what you're doing is transforming odd functions into sections of a bundle. So let's do some pictures. So too abstract otherwise. I have the pictures way at the end. I'm going to change that. I'm going to do the pictures now. But is this clear? So what the idea is, this space is a trivial bundle. The sections of a trivial bundle is what we call functions, right? The functions from M tilde to R are the sections of the trivial bundle. When we quotient the bundle, this line bundle, we're kind of doing like gluing a Mobius band. That's the idea, right? And now the sections in a Mobius band They correspond to odd functions on the bundle, but they also have a zero set. You can talk about another set of a section. And in the case of the Mobius band, it crosses one point, which is not separated. So let's do examples of line bundles. That will be the first one. So examples. I'm going to give you a few examples in other contexts. So the first one is over S1. You see, S1 is not really like R3 minus gamma. It's a closed manifold. But I think it's worth looking at it. So one bundle is the trigger bundle. So I'm thinking I'm identifying this side with this side. So this is an S1, right, the center. And then the bundle has sections which look like this, because I have to glue this bit with this bit. So this is the trigger bundle. And what you can note is that the number of zeros is always even. It has an even number of zeros. But then there's another bundle, and there are only two bundles, whereas one, which is a Mobius band. And in this case, the section will look like this, because this point identifies this point. So here you always have, obviously, Mobius bundle. Part. Okay. So you see here, because it's an even number, the set of zeros is separated. It divides into this part and this part. But here is not separated. This is one. So on a torus, you can do the same thing. You can have a trivial bundle. So trivial bundle. And by the way, now we're in dimension 2. I cannot really draw the bundles anymore. So this is just the base space. But you can see that a nodal set of a section will have to be like this, something like that separates, right? So zeros of sections. But you can do a Mobius bundle over the torus, right? So, what is the idea? It's a line bundle, and every time I go around a circle, if I look at the fiber, I see this. I see the Mobius bundle. Right? So if I look at the one-dimensional, the restriction of the line bundle over S1 gives me a line bundle over S1, and if I go around this direction, I see that one. Does that make sense? So this is an attribute. The bundle, and here the zeros will be, because every time you go from the Mobius band, you see one zero. So if they're put together nicely. But truly, on S1, you only have these two bundles. These are famously the only two bundles that you can construct over S1. But in the torus, you have many more, because now you have an interesting homology. So I can do a bundle that sees this homological class, or I could do a bundle that maybe sees this homological class. Or I can take a combination of them and make a bundle for that, and so on. Okay. So every homology class of curves in T2 has a bundle whose sections are in that class. Okay, so what does it look like in the Plateau case? By the way, so remember how we constructed this bundle? We first did a double cover and then quotient the trigger bundle via the action of the double curve. I can always take a curve in this double curve, or I can always take a curve on my base space. And then the restriction of the line bundle to the curve has to be either a cylinder or a Mobius band. Right? Because if I restrict a line bundle to a curve, I have only one of those two. So it's about classifying the curves to understand what the bundle does. So, so a bundle over R3 minus gamma. Say your gamma is maybe like this. I haven't, it's not knotted. That's irrelevant, but it's not. So the bundle that one obtains, because we send the generators, so this, how can I call the generator? C. That's a bat. So C is the generator. Then the bundle has to be non-trivial over C. On the other hand, if I take another curve here, let me call it G. This is, well, G is bad because it's not a generator. So, I don't know, cap. This is not a generator. So here, the bundle over C is Mobius band. And here, the bundle over kappa is a cylinder. So geometrically, why is this helpful? Well, remember that every time you have a section of a Mobius bundle, it needs to have a zero. So that means that the nodal set, or the zeros of my section, intersect all the curves that are, for example, homotopical to this one. So there's going to be, maybe I can pick in purple, there's going to be some zeros set there. If I pick another curve, there's going to be another. And if you think about it at this heuristically, you will expect to see a surface whose boundary is. So that's the idea. Right, that's the idea. Okay, I have 10 more minutes. So I think I can finish what I prepared for today. Any questions about this? Okay. So why is it helpful to analytically now? So geometrically, I hope I convinced you that this is a good space to work on. But also analytically. So this comes from the fact that the energy is symmetric, right? So E of U is equal to E of Z. Or maybe I should put 2. So if I multiply a function by minus, the energy is the same because because the energy was this, which doesn't care if it's positive or negative, just the models are negative. And then this function U is symmetric. W is symmetric. So these type of functionals, they're suitable to be defined in the context of a bundle, of a line bundle, because you don't really care what's positive and what's negative, you just care how far your effects is. So therefore, also shows 1. To L of R2 minus 1. So that is to say, you can define we have an ocean of, say, Allen-Cahn sections. There are sections that are critical points of the quotient energy. Okay, and this is, of course, a kind of an abstract construction. In practice, every time you pick a small neighborhood, what you see is just the regular Allen-Cahn, because you can pick a trivialization of your bundle, and then you just have a regular function. Okay. I think the relevance of the abstract construction, though, is just to know that you're working in a unique setting that makes sense geometrically. But in practice, a lot of the work has to do with just regular PDs. Yeah, this is something I keep struggling with when I'm talking to people in PDE. They focus a lot on the bundle part, try to understand. And the point is that is the opposite, right? We kind of forget about it. You have to forget. You have to be careful when you construct it, but then in practice, you just forget about it. Locally, you're seeing solutions of the Allen-Cahn just as before. Of course, near the boundary, you cannot do this. Near the boundary, you always have the boundary. Because any open neighborhood that contains a part of the boundary will have the noise on them. So that's what we work. So yeah, I just want to summarize and then state the main theorem, which I haven't stated yet because I can't without bundles. So what's the main theorem? But before summarizing, just kind of give you a diagram to take the view. We have surfaces whose boundary is gamma. They correspond to U tilde R, where the function is R. This is my U boundary. And such that the zero set is an overcover of sigma. And then this corresponds to U, which is a section of L gamma, and the set of the section is sigma. So we have a correspondence between surfaces with boundary, arc functions on a double cover, and finally sections of as the correspondence. That's what it is. And depending on what you're doing, you might want to emphasize one setting more than the other, but they're all equivalent. Okay, good. So theorem, main theorem. So I'm going to state the part that is done by student. There is a minimizing section, an minimizing section U of L such that the level set converges to a surface sigma as epsilon goes to 0, and sigma is smoothed away from gamma. And then what we did with Steven, so this is joint with Steven, Lynch, is that in fact sigma is embedded up to gamma, and it's a solution to the problem. We call it embedded photograph. It has better energy, better area, smallest area among all surfaces that have gamma as a smooth boundary. Okay, I kind of finished in time. Let me just say a few words about the dimensions. Okay, this is the theorem we're gonna discuss tomorrow and after tomorrow. How to do this. This nice theorem about the boundary cannot be true in higher dimensions. So let me just discuss that. So this is a remark. So if you take, for example, gamma, say an embedded RP2 inside of 4, right? So boundaries always have codimension 2, boundaries of surfaces. Then you can solve the Plateau problem, right? You can solve the Plateau problem. You can find sigma, which is smooth away from minimal surface that is obtained when you attempt to minimize the area of all the surfaces that have this. And it's going to be smooth inside because the regularity theory inside is the classical one in R4. So you're minimizing, you have all the curvature estimates that you want. So you can do this with currents and other ways. But the point is that because it is smooth inside, it cannot be smooth at the boundary. Because if it was smooth at the boundary, then you could orient RP2, right? Because it would be the boundary of something that's smooth. Right? That's more or less the idea. Of course, you can argue that maybe this is non-orientable, so you cannot do that. But the point is that at the boundary, you always have a direction, a preferred direction, right? So you will be able to construct a normal vector level. So you can prove this more formally, I think, by doing Euler characteristic computation in the RP2. So then sigma about B will along. No. So what happens there? Because actually sigma exists. You can solve the Plateau problem in this more abstract sense, and you will obtain a stable minimum surface. So there must be a singularity at the boundary. So the question, one interesting question is, what happens when you blow up the singularity at the boundary? Right? There has to be a non-orientable area minimizing minimal cone with boundary line, a plane in this case, in R4. So maybe a picture. So you have your RP2, yeah, and then you found there's a similarity here. When you do a blow up along this line, so your boundary has dimension 2. So you're going to obtain a flat R2 inside of R4, and there has to be a 3-dimensional cone, which is non-orientable without boundary, and that is area minimizing.
Wow. Yeah.
Yeah. This is the proof. The proof is that you can solve the Plateau problem. It's a smooth in the interior, so the singularity has to be at the boundary. And then there's this cone. So Brian White has a conjecture of what this cone has to be. Is a cone. So now the link of this cone with a S3 is a minimal surface in S3, which is kind of a nice thing. And then his conjecture is that there is this specific Mobius band that is minimal in S3 that has to be the link with the cone. So the Mobius band is really nice. You can construct it using geodesics. So it's a Mobius band that's spanned by geodesics. So it's like a ruled surface. It's non-orientable though, And that's a big problem because that means you kind of run out of tools that you can use to prove that the thing is minimizing. Because the tool to prove that something is minimizing is usually calibrations. But calibrations are orientable things, orientable objects. Okay, so yeah, that's a conjecture that cone is minimized. So this is quite interesting because it's still something where you can draw pictures, right? Because you're in a street, you can't kind of like do a stereographical projection, but it's still open, and it's about non-orientable minimal surface. So here in Granada, there's a few people that have worked in non-orientable minimal surface.
What generality can you solve a Plateau problem of this type? I mean, R4, what kind of, how is the general existence of solutions? How can I check the boundary?
How can you check? What do you mean?
Can I check the boundary? How general could the boundary be?
Oh, anything that's closed, I think, could be a boundary. Anything that's a topological boundary could be a reference, right?
So I take a smooth two-dimensional manifold of R4, compact, and then I can solve.
Yeah, I think so. Yeah, because you can do the line model construction and then the sections that will exist, right? And then the point of the sections is that they always have zeros because the boundary is non-trivial. So the energy is always bounded from below because they always have a model set. So you will converge to something that's not empty when you try to minimize.
The other question is it true that now we go to 3 dimensions in ambient space is 3-dimensional? Is it true that every solution of the Plateau problem can be constructed this way?
Right, so that's one thing that I'm working on with Manuel Pino, a postdoc in ETH named Marco Badran. We're trying to do the Picard for this setting. So if you have a non-degenerate solution of the Plateau problem, independently whether it's minimizing or not, you can have some index, but as long as it doesn't have a kernel, the Jacobi operator, then you should be able to construct a solution to the Allen-Cahn.
Find it as an Allen-Cahn limit.
Yes. So there's a few open questions which I will talk about tomorrow. This is one of them, right? But I can tell you a couple now. The things that I did, which are in the opposite direction, I think are also interesting, which is if you have a finite index number of solutions and the epsilon is going to 0, what is the limit minimum surface that you obtain? Can you say something about the boundary or not? You know it's going to be smooth in the interior, but the question is what happens with the boundary. That's one question. The other is what are the models when you do blow up, right? So when you do a blow up in R3, you have a boundary aligned. So you're talking about entire minimal surfaces whose boundary is aligned, which is something you've worked on before. So that's a good question, I think, is can you, for example, no, first of all, the obvious solutions, which are the half line in R2 and the half plane in R3, one has to prove they are minimizing. I know how to prove now how the half line is stable. And again, I will talk more about this tomorrow. But I haven't proved that it's minimizing. Yeah. Then the other question is, can you characterize, can you prove that the only stable in dimension 2 is half a line? Open question. Then when you go to R3, you start asking more interesting questions because of the existence of the enapper. So you can ask, does the enapper exist as a solution of this section? Yeah. And I think the interesting thing is that I will guess the enapper view as a section probably has index. You see, because the enapper is minimizing with respect to orientable perturbations, but is not minimizing mod 2, right?
No.
Yeah, so there's a possibility that it's not, that it has an index that appears, because in the function setting, you can do things like, for example, a solution of the Allen-Cahn that's like this has index, because as a function you can easily separate this into this. It's a continuous deformation, so the index gets to see that. So you add an index by adding this extra dimension. So yeah, maybe the enapper has index 1. I don't know. That'd be interesting to see. And there's a problem that will require a lot of work. Though. Someone has to sit down and really study the Jacobi pair of the enapper and do all the computations. But yeah, I think these questions are interesting. And then in higher dimensions, of course, even in the minimal surface case, already in dimension 4, we don't know, because the examples have to be non-orientable, and this is hard.
Is the enapper the only possible configuration that you can find in the limit? Yes.
You mean in R3?
In R3.
But this is your theorem.
Yeah.
Yeah.
The thing is that if you rescale, you will always find quadratic area growth.
Yes.
So it has to be in there.
Yeah, you will find something that has control area. So it's either an upper or the half plane. Yeah.
Esa cobertura está abierta,
No. With quadratic area growth.
I
It's
know,
not,
I mean, this should be true in general.
The open question is it true that stable values by allowing minimal without knowing anything about the area growth? It could be the helical, half of the helical. Could be the only non-quadratical thing.
Oh, it is a solution, right? Half the helical.
It's a solution, but it's not always the unique solution.
And it's not stable. Is it stable?
It's a
It's
stable.
stable.
Half the
helical is stable.
Oh, I see. So yeah, so that's a good point. I think in this case, it's interesting because you see when you say you have a sequence of index 1 solutions, sections, whose nodal sets are converging to a minimal surface. If the enapper has index 1 as a section, then in the limit I can prove things are smooth because something that has index 1 is really stable in almost everywhere. So you can truly say something about the limit of things with index if you are able to rule out the enapper as a possibility of a stable. Yeah. But this is, I mean, I have no idea. I think heuristically you can make arguments of why the enapper has to be stable and why it has to have index. So one has to see what happens. I think if it has index 1, a lot of things will be interesting. You can say more than in the minimal surface case, but let's see, maybe someone can work on this in the future. Yeah, so I'm done. Thank you. See you tomorrow.
Thank you. Nice. Any other question?
Yeah, you can ask me over the ladder.